postsynaptic potentials that are caused by neurotransmitter chemicals can be either depolarizing, often but not always resulting in an excitatory postsynaptic potential, or EPSP, or hyperpolarizing, resulting in an inhibitory postsynaptic potential, or IPSP. Postsynaptic potentials generally move passively along the dendritic membrane, gradually becoming smaller as they spread. Therefore, the postsynaptic potentials from more distant synapses will decay more than PSPs from synapses closer to the integration zone at the axon hillock. The postsynaptic potentials produced at most synapses are usually well below the threshold for generating postsynaptic action potentials. How then can synapses transmit information if their postsynaptic potentials are subthreshold? Suppose that two excitatory endings are activated, causing local depolarizations of the cell body. Taken alone, neither would be sufficient to trigger an action potential, but when combined, the two depolarizations sum to depolarize the membrane in the hillock region to threshold. When inhibitory synapses are active, the membrane potential tends to be...
Did you see what that little, just in sort of a catch it, did you see how the impulse went here and then it jumped to here and then it jumped to here? Okay. What was going on there?
It was the neuron VA.
Yeah. So these are Schwann cells or oligodendrocytes if we're in the CNS that are myelinating the axon, and they increase the speed of impulse connection so that the impulse just jumps. It just slides right over the fatty myelin, and depolarization only occurs at the node that runs VA, as Gordon said. Nice example. Sorry, just want to make sure you notice that.
To be stabilized below threshold because they induce hyperpolarizations or subthreshold depolarizations that cannot reach threshold. These postsynaptic effects also spread passively, dissipating as they travel. Because some potentials excite and others inhibit the hillock, these effects partially cancel out each other. Thus, the net effect is the difference between the two. The neuron subtracts the IPSPs from the EPSPs. Postsynaptic effects that are not absolutely simultaneous can also be summed because the postsynaptic potentials last a few milliseconds before fading away. The closer they are in time, the greater is the overlap, and the more complete is the summation, which in this case is called temporal summation. The summation of potentials originating from different physical locations across the cell body is called spatial summation. Only if the overall sum of all the potentials, both the EPSPs and IPSPs, is sufficient to depolarize the cell to threshold of the axon hillock is an action potential triggered.
Does that give you some sense of the complexity of the brain and how it works? That there are these millions of nerve cells that are synapsing with one another, perhaps hundreds or even thousands of synapses, and that all this information has to be integrated over space and time within the brain for the final outcome to occur. It's very, very amazingly complex. We can study it, and look at one neuron and look at one synapse and understand it, but to understand how the brain functions as a whole, you have to really think on a different level. Right?
I've got a question for you.
Yeah.
So how much variability can you have in a single PSP, like in a single firing? Because it's based on neurotransmitter release, do you see much variability in neurotransmitter release and the change of voltage?
Yes. So if you kind of remember when we were looking at those tracings where of a stimulus and a response of a single excitatory or inhibitory neuron, in the lab that was an electrochemical manipulation or electric manipulation of the presynaptic neuron. The increasing intensity of the electrical charge led to a greater magnitude PSP. That is reflected by the release of greater numbers of neurotransmitter molecules, so more neurotransmitter vesicles are joining with the postsynaptic membrane, and the opening of more sodium channels.
So that's what you were
Yes.
being graded.
Yes, that's
But-
what's graded.
So then with the action potential, which is not graded, what affects the different amounts of neurotransmitter release by the end of the neuron? Is it just what's downstream, or?
You mean by the stimulating neuron or
Well,
the...
since the action potential is the same, what causes variability in the PSPs?
The rapidity of firing, how frequently the action potentials fire,
Okay.
right? So if they're happening at high frequency, you'll get more neurotransmitter release at the end and a greater stimulation of the next neuron down the line,
Okay.
right? So for action potentials, it's all about frequency, and for PSPs, it's all about magnitude, okay? Good question. Really quickly, a little animation on myelinated impulse conduction. Here we go. So here's what it might look like without myelin. Kind of slow change, positive ions going in and then getting cycled back out again, right? And here's what it might look like. What we call saltatory conduction, myelinated conduction. Saltare means to jump or leap or dance. So the impulse is jumping from one point to another, going much faster. So myelination increases the speed of impulse conduction.